Polynomials and polynomial functions play a central role in algebraic signal processing. This section is a short aside to introduce definitions that we will use later on. Things are about to get insidious. We are going to have several different objects, all of which are called polynomials, but their subtle differences are precisely what is important to be able to understand the foundational concept of algebraic signal processing. Our first polynomial is a polynomial in an algebra. Given an element a of capital A and a set of coefficients h sub k in the field f, a polynomial is another element of the algebra. We denote this element as p subcapital A of A and define it through the use of the usual polynomial expression. This involves several terms, in each of which we have the algebra element A multiplied by itself k times, and the result factor multiplied by the coefficient h sub k. These different terms are then added together. This is what you should have expected for an expression that is called a polynomial. There is nothing new here. Nevertheless, there are two important points to emphasize about this polynomial. The first is that p subcapital A of A is an element of the algebra A. We know that this is true because p subcapital A of A is constructed from A by using the operations of the algebra. The second point is precisely this, that p subcapital A of A is generated using the operations of the algebra. The polynomial is not just a symbol, as was the case when we defined the algebra of polynomial. It is a concrete representation of a concrete set of operations. This distinction, already subtle, is made even more subtle because the operations that generate p sub A of A can be symbolic. In any event, symbolic or not, the polynomial p subcapital A of A is an element of the algebra A that we obtain through a concrete set of operations that we perform on the element algebra A. The reason we want to emphasize the use of the algebra's operations is that we are going to be interested in writing polynomials on different algebras. When we change the algebra, it is possible that we use the same coefficients, but although this may result in two polynomials that look the same, the polynomials are actually different. To drive this point, suppose that we consider an element A' of a different algebra capital A'. Even if we retain the same coefficients h sub k, the polynomial p subcapital A' of A' is a different element. This is not only because A and A' are different, but also because we are using a different set of operations. We are now using the operations of the algebra capital A'. Notice that this can get obscured with the usual notation because it is implicit that the operations are performed in the right algebra. The important point to keep in mind is that polynomial expressions that look the same can represent different operations, like the operations on an algebra A, and operations on a space of endomorphisms of a vector space, as you may foresee. As if we didn't have enough polynomials already, we have to introduce yet another concept. This is that of a polynomial function over a field. This is notoriously different from the others in that it does not involve an algebra. We consider coefficients over a field along with a variable lambda that takes values on the same field. The polynomial function p sub capital F is the function that maps lambda to the value p sub f of lambda defined by an expression with the usual polynomial terms. In each of these terms, we have lambda multiplied by itself k times, with the result being further multiplied by the coefficient h sub k. and the different terms added together to obtain the polynomial's evaluation. This polynomial is the one that should be most familiar. It is just a function of lambda, mapping values on the field to other values on the field. It is, we must repeat, a function that is defined in terms of the operations of the field. There is no algebra involved here. By the way, if you notice a resemblance to frequency responses, this is not coincidental. In fact, it is rather the point. But this is just an aside comment at this point. In our discussions so far, we have considered polynomials of a single variable. Generalizations to polynomials with multiple elements are ready. If we consider a set calligraphic A made up of R elements of the algebra A, we define the polynomial P sub A of A as the summation of different terms, each of which has the different elements of calligraphic A raised to different powers, and scaled by corresponding coefficients. This polynomial is associated with coefficients h sub k sub 1 through k sub r that are drawn from the field f. This polynomial represents a concrete set of operations performed on the elements of the set calligraphic A to obtain another element of the algebra. The polynomial P sub capital A of capital A. We point out that in this definition the algebra is assumed to be commutative. If the algebra is not commutative, the order of the products matters and the polynomial takes on a different form. This is not unimportant. There are interesting algebras that are non-commutative, but the extension is straightforward. Likewise, we can define the corresponding polynomial function with multiple variables lambda sub 1 through lambda sub r. If we use the same set of coefficients, this polynomial function is the same expression as before, in which the different algebra elements a sub I are replaced by variables lambda sub I. Nevertheless, the similarities of the expression should not distract from the fact that the objects they represent are different. This second expression is a function of the variables lambda sub I. It takes different values when we instantiate different variables. It is also an expression that uses different operations. The polynomial on a sub I uses the operations of the algebra A. The polynomial on lambda sub I uses the operations of the field.